Okay, we'll start continue on information geometry. So we'll first review some basic concept, and then basically we'll have two examples today, and uh, uh, and then and discuss some computational details. Um, uh, I will not cover Bregman divergence as announced before, because it's probably better to use some concrete example to try to understand the concept first, and then next week. I mean, next week we'll not meet, but after so 2 weeks from now, in Friday, we'll move on to the week 3 lecture. So this is basically the review. So the Kullback-Leibler divergence is defined this way, and this particular function is called entropy function. The information projection. So this pi is a kind of a subset, a subspace, uh, and then the projection. So in the last time, actually, I made a mistake. I incorrectly state that this is M projection, but it turns out that the literature used the I projection. So we'll use the follow the convention. So this is I projection, information projection. Uh, uh, of this Q onto the space. So you can think of this pi as a subspace, and Q is given. Okay, Q is given outside the space, outside the subspace, right? And one of the important family of subspace is this particular type. So this is a mixture type, uh, basically uh, uh, mean condition constraint, expectation constraint, and so this is closed and convex, and then some theory says that you can under some conditions this minimizer exists and unique, and furthermore the solution takes the exponential function. So exponential, so this is actually exponential tilting, right? So this is the baseline, Q is the baseline, and then you just adjust from Q to the amount that the expectation is equal to, its expectation is equal to the given alpha. Okay, so you can see that there's a one-to-one correspondence between the parameter zeta and parameter alpha, right? So parameter alpha is a mean parameter or expectation parameter, and parameter zeta is called canonical parameter or natural parameter. So if you change alpha, right? If you change alpha, then zeta will change. So this is more like a toy example. So if you, this is a baseline, normal 0, 1 baseline. And if you, of course, this has a mean expectation is expectation of x is 0 and variance of x is 1, right? But now you want to impose a particular constraint. So first moment and second moment constraint and minimize. Okay, so this is a baseline. Right? From the baseline, you impose a condition that its expectation up to second moment satisfy this for this given mu1 and mu2, then the solution turns out to be just shifting. So you basically shift your baseline function in the E, right? E geodesic way. So this is basically the surface statistics. So this is geometry of eye projection. So this N is this one. So this N is mixed. So this is a set of all Q, set of all P, whose expectation, okay, Q, right? So given Q's, whose expectation of the surface statistic, here is T, is equal to P. So any element here, any element in this line basically has the same expectation with respect to T, right? With this particular given P. So this is one geodesic, this is M geodesic line. And then what is orthogonal to this one is an exponential family. So this E is an exponential family. Basically, this is an exponential family of Tx, right? And so so this P star turns out to be intersection of these two spaces. So it should be in the exponential family and satisfies the this M geodesic. Okay. So yeah.
So in this time, we introduced the space NP, and in the previous slides, you introduced the L alpha.
So N is actually right. So yeah, notation is I just copy this figure. I didn't create. So this guy is actually L alpha, right? Yes. Okay. This guy is L alpha. So I just copied. So okay. So the beta. So then the line here is E geodesic, and the line here is M geodesic. Okay. So that is the main result that we studied last week. And so the eye projection of Q onto L alpha is that we search, so the Q is given, right? We search over all P in this space, okay? And then basically the projection is appears when this is in the geodesic, I mean, right? So this one is indeed this one, this intersection of the L alpha and E. And so if D is a Kullback libel, then the geodesic between P and Q, P star and Q is E geodesic given by 1. So what is 1? 1 is this one, right? So the relationship here basically says that P star and Q is E geodesic, right? So that so it is called E projection. And once this P star is obtained, uh, uh, basically if you choose fix alpha, then you fix beta, right? And so, but if you allow alpha changes, then basically you allow theta changes. so what does that mean? Well, so let me explain different way. So basically, this one vertical, line basically represent the value for given mu. I mean alpha, right? So that's a mean vector. So basically, this mean vector will have a different position. Depends on if you, right? If you move your alpha around, if you move alpha around, then you will have a different position. Then for each one, you will have a different, basically different p star. Oh, sorry. Okay, right. So then, and now what really matters is the so which vertical pole you want to choose. Turns out that you want to choose the one that has a p hat in it, right? So you want to choose the one that coincide with your empirical mean of your sophisticated statistic. So that is actually M step. I mean the M projection. Okay, so that's actually coincide with the maximum likely estimation for exponential family, and so it makes sense to call it M M projection because it's maximum essentially maximum likely estimation. Okay. Okay, so that's the review. Okay, any questions? So now we're going to move on to the section 2, which is the really important result example that's particularly relevant to calibration estimation in survey sampling. And also in causal inference, we have covariate balancing, all these, directly related. Okay. So, okay, let's assume that you have a discrete measure. Okay, so discrete random variables kind of thing. Or you assume that, okay, you even though it's continuous, you don't care, you don't worry about the realized sample outside the realized sample support. Okay, so this is a given. Okay, so you observe x1 to xn, and you want to basically develop consider distribution on this particular data point. And so then the problem reduces to finding out the weight, constructing the weight. Okay. And so the weight, the condition constraint that we want to impose is the mean constraint. Okay. So we want the weighted mean of the surface statistic, which is B, equal to the mean of a population. So this is a kind of given population. So or known external, which is different from sample mean. Okay, so you suppose you have extra information from census or whatever, know the marginal mean of X variable. I mean, certain function of X variable, then you want to impose that information to your estimation procedure and consider it as a constraint. Okay. So the question is, given a sample, how to find the optimal density, satisfying the moment constraint info. Okay. So this is exactly the eye projection problem. So the space that we are interested in is the calibration space. Okay. So basically, we our density uh, is a weighted version, right? So basically weighted distribution. So but the weight indeed. So what do you mean by this? This is nothing but equal to actually because we our definition of a p, right? Our definition of a p x omega is just putting weight omega I for each data point xi. So then this summation indeed is just computing uh, weighted weighted average. Okay, so this is a constraint, and then the objective function, right? The cost function in the optimization is the Kullback-Leibler. So the Kullback-Leibler. So because the p, so this particular p is this class, right? So this class. So then that means we can actually uh, uh, work out, so write down the specific form of this Kullback-Leibler divergence as a summation, something like that. So which is indeed this. Okay. So as a function of omega, it's just a constant. So this is basically equal to 1 because this one is just constant, right? So, Injun, you have question?
Oh, no.
Okay, okay. So just the log p I had is 1 over log 1 over n, which is constant. And so the summation, second summation is just constant. So then that means you basically have a constant so the first term is minus entropy. So you are subtracting entropy. So minimizing this is maximizing this, right? So that's why it is called maximum entropy method. Okay. So maximum entropy method is just try to solve some optimization using the entropy as an objective function. So for example, this kind of problem has been investigated in many different areas, like ecology, and they also have their something called maximum entropy estimator. But specifically in survey and actually this guy Hai Muller is a political scientist. So he works for Department of Political Science at Harvard or Princeton, something like that. So anyway, so he in his paper he tried to come up with some weighting as a as an optimization problem. So it's very straightforward problem. So maximize the entropy, right? Which is this one, subject to calibration. Okay. So that is, and then nice thing with this approach is you don't really have to worry about the whole. So you translate the original problem into weighting problem, and the weight on the sample, right? So then it's just so now your problem is finding omega in the sample. That's it. And so then how to solve this? This is very standard constraint optimization problem. And so you can use Lagrange multiplier method. So this is a mean constraint, and this is a normalized constraint. Okay. And then taking the derivative over L with respect to omega and setting to 0 will give something like this, right? And there's actually additional constraint like how we want to make sure that omega I is positive, something like that, right? Or at least not negative. But because I have some comment. So in this particular choice, you don't have to worry about that because it'll never get negative weight because of the particular form of the uh, uh, optimization function. Okay. So, log is not defined in omega. I mean, not defined on negative values, right? So then whenever as long as you have any value exists, then the solution will never take negative values. So that's the main one message. And okay, so this is a very standard problem. This is sometimes called called KKT, right? KKT I would condition. So so basically the gradient of the Lagrangian with respect to the decision variable, which is omega I, must be zero at the optimum. So this is explaining why we put zero, right? Should be because this is the kind of boundary point. I mean, optimization, point. And then there's some additional details like so this was actually a necessary condition, but it can be actually also sufficient if it satisfies uh, some additional condition like objective is strictly concave and constraint are fine, then these KT conditions are also sufficient, not only necessary. Okay. So anyway, if you if you solve this with respect to omega, then you will get this form. Okay. So G inverse is just the inverse function of G, and small g is a first order derivative of capital G. Okay. And now, what is G omega? Omega log omega minus 1 minus omega. So G prime is what? You can actually see that this is log omega. Okay. So this one. And so the inverse function is also easy, right? So the inverse function of log is just the exponential function. So then your weight is basically exponential function of G pi transpose lambda times divided by normalizing factor, right? So this normalizing factor is, we can call it C, C lambda. But you can see that the main reason, so, okay, if you look at this, I intentionally put red color on omega and lambda, but didn't put red color on alpha, because alpha is not really a parameter in some sense, because this is, right? If you change, so there's a mu, if you change mu, then you change lambda. So there's a one-to-one correspondence between mu and lambda. So dimension, right? If you think of dimension. But this is not a parameter, alpha. Alpha is just normalizing constant in the sense that it's just automatically chosen if once you determine your lambda, right? I mean, so this is, so you don't have any control over alpha, over choice over alpha, because alpha must be chosen from the choice of lambda. So that's why, so as you can see that this guy, right? This guy is completely determined by lambda. And then notice that this weight omega I star lambda in equation 11 is an exponential tilting of the empirical distribution. So this is the empirical distribution, which is 1 over n, right? And then you just multiply some factor, exponential factor that adjust. So if lambda, for example, if lambda is 0, that means what? if lambda is 0, that means you have no adjustment. So if you are lucky, right? If you're lucky, and so sample mean happen to be equal to the population mean, then that means you don't have to do any adjustment. But otherwise, you need to do some adjustment. And so that is the basically what this is. What is this is? So you can in survey sampling, basically this p hat is the original rate, and omega star is a final rate, right? And so this is a more like an adjustment factor due to calibration. And so that really matches well with the survey sampling, concept. And now let's check this more carefully. So by four, what is four? Four is probably calibration, right? So this by the definition of omega, right? By the constraint. So given mu k, right? Given mu k, we will choose lambda to satisfy this equation, right? So that is the basically calibration equation or calibration constraint. And now this particular function is an exponential function and normalizing factor. Okay. And then interesting part is that this function here can be viewed as a differentiation of g lambda, because what is z lambda? Z lambda is here, right? So because this is a summation of exponential function, and so if you take the differentiation of z lambda with respect to particular lambda k, then you get this particular vector function pk goes outside exponential function. So you get you can write this way. So that means you can write the lambda, I mean mu k as a partial differentiation of the log z. So that is interesting because what is the log z? Well, you can write it as an exponential function of pi transpose lambda minus phi psi lambda. That's what we used in the definition of exponential function, right? So that means log, so phi psi lambda is log z lambda. And so if you define this way, you can write, you will have this form, right? So this psi lambda, we call it cumulative generating function, right? Cumulant generating function, or free energy, or potential function. So we'll use the term potential function. I like the term potential function because basically it if you differentiate, this function has the property of giving out the mean, giving out, providing the expectation if you take the differentiation. Okay. So you can see, so now I'm going to explain a little bit. So basically this equation is just a vector expression of this equation, equivalent, right? It's just so that means this is, because this is a calibration equation, this is actually calibration equation. Now, another observation is that because we know the form of the omega star, we plug in to the original Lagrange multiplier and simplify. Then basically this is the original one, and then this guy. So what is this? G omega is omega log omega minus omega, right? And so, and what is omega? Omega is this. So this is omega I star. This is what? This is log omega star, omega I star. Okay. And then minus, well, we don't have to worry about the minus or plus summation omega I star uh, because this is essentially constant. This is 1, right? And then you have, this is on also what? Omega I star, right? Okay. So then as a functional, and then what? Okay, so this is just a writing expression, and then what? Then you have a nice cancellation. Where? Because this whole thing cancels with this one. Okay, so you end up getting only this term and this term. Okay, so that is this one, right? Okay, so basically now by plugin, this is function of lambda only. Function of lambda only. So you basically express your optimization for lambda. So because this is basically dual optimization, instead of trying to, right? I mean, so originally we are interested in computing, determining omega, but lambda is a dual, kind of dual parameter. So the turns out that you are solving a minimax problem. Why? Because what is this? This is actually L omega star lambda, which we just wrote here, right? So no head, just omega star lambda, of course. So this is more like a saddle point problem. You basically solve minimax. Okay, so once you obtain solve this, so given, right? This is given, right? Given. So basically, given mu and given g, right? Given g, you can actually figure out uh, uh, from g you can compute psi lambda, right? Which is potential function, and solve this problem to obtain lambda star, and then you can find final weight. Okay. So the primal problem is the, so see, in the very beginning, I this is the description of primal problem. So primal problem is the optimization problem, actually constrained optimization problem with respect to omega. Okay, and now dual problem is unconstrained. So primal problem is the constrained optimization problem with respect to omega, right? Is solved by its dual problem in 14, which is with respect to lambda. Okay, so omega is n-dimensional, right? Omega is a vector for the sample. So usually the sample is element, right? Sample size is element size. So your sample size can be like maybe 5,000, right? 10,000. It's fairly large. However, this lambda is just the number of equations. So the m dimensional. The number of equation can be like maybe 10 equation, 50 equations. So relatively small dimension. So usually that's if n is much smaller than n, then dual problem is much easier to solve than the original problem. Okay. Okay. And then let's check whether this Pythagorean theorem holds. So we know in theory, right? We already saw that the I projection will satisfy Pythagorean theorem. And now let's check whether it is really true. Okay. So this one, right? So this is a Pythagorean theorem. So Kullback-Leibler law between P star and P hat. P hat is just remember P hat x is just 1 over n for xi, right? So then basically this is just a definition of Kullback-Leibler. And then a second equality, we know the form of the omega star, right? We know the form, which is this form. So log omega star is this form. And then we know that this one is a calibration equation, mu. So we know that this will be this one. And also for any P in this QU, in this space, we can do the same thing. And so basically this is the definition, right? First line is just the definition. Second line is we know the form of the omega I star. So which is this one, right? And then this guy equality comes from the fact that it satisfies the calibration equation. So P star belongs to this space, right? And so you can see that this guy here is this guy plus this guy, because no, the other way. PP hat. Okay, this guy, I see. This guy, so this guy is equal to this guy. And so if you add these two, if you add this, then there's a cancellation. Okay, cancellation. And then the only thing left is this one. So that shows the, indeed satisfy the Pythagorean theorem. Now, let's take a look at this form again more carefully. So this G star is just omega minus omega log omega. And then because of the form, we have this form. Okay. And and then this guy is this guy, right? And so we can view it, we can now view it as a function of mu. Okay. And then this is essentially recall the definition of a convex conjugate function. Basically, this is a convex conjugate function, right? So the dual relationship between psi and phi has this, and so turns out that this phi function satisfies after some algebra. You can see that this guy satisfies this. So there's actually a nice dual convex conjugate property. So here's a summary. The okay, is it too maybe I'm too fast. Why not? Okay, is it okay? Okay. So yeah, so mu and lambda are connected. So you cannot really. So when you compute the differentiation, when you evaluate the differentiation, you need to take care of this differentiation, right? So you need to apply the chain rule, and then if you apply the chain rule, turns out that you don't really have to evaluate it because it's actually cancels. You have a cancellation, and so then it gives back to your original parameter, and so that gives a nice uh, dual relationship. So so basically, previously you have this one, right? Psi lambda. And so there's a very one-to-one relationship. So how you can obtain lambda from phi, or I mean from mu, or obtain mu from lambda. So this is a kind of a summary. Uh, so here so you can think of this is a kind of a point mass measure in your sample, right? If you view it as so this measure as a p hat measure, empirical measure, then this is exactly same as what we discussed in this example, but this is more general. So so basically, this is the potential function, right? So this potential function gives the moment, and then from the potential function, you can construct a dual function, right? Which we can. So last week one class we called it psi star, but we now use this another notation, phi. So then this is how you define the convex conjugate function or Legendre pair. And then this lambda is a e-coordinate. Remember, this lambda turns out to be this one, right? So your coordinate system is in the exponential family. So this is e-coordinate, while mu is the m coordinate. And if you turns out that you can write this Kullback-Leibler function as a function of your potential functions. If you do that, this is actually a Brakman divergence. So that which we'll cover next week. I mean, next class. So basically the core. Remember in our Kullback-Leibler, this one, this is psi is well, this is the psi is this one. So actually, this potential function determines the whole space, whole everything, basically, right? So this one, sometimes this psi is called the generator because it basically create the whole subspace. And basically this guy create all the coordinate system later and Pythagorean theorem. But we'll see the next class. So Legendre map gives the one-to-one identification between natural and mean parameters, right? And because psi and phi are convex conjugate, both lambda and mu chart coordinate systems are flat, yielding a dually flat EM geometry that underlies projection algorithms and Pythagorean identities. So that is the main takeaway. We'll have a short break, 5-minute break, and then move on. Okay. Yeah. Well, so the information projection. So this is another example use of information projection, which basically is a tool to incorporate how to incorporate information, available information. So this is you are interested in estimating the parameter, but you don't want to make a strong model assumption. But you just construct the equations that defines the parameters. Okay. If you do that, then this is a semi-parametric model because, okay, so suppose your parameter is just y and y square. Okay, so this is your parameter. And then there's a lot of many different distributions that have the same first and second moment, right? But you don't care. You just want to just focus on this parameter only, and then how to estimate it from the data. Interesting part is that so if you have a two equation, I mean two unknown parameter and two estimated equation, then it's not really interesting. But in some cases you have more equations than parameters. That is actually having incorporating the extra information. And so that is a really important, popular problem in econometrics and causal inference and these areas. So then this is basically semi-parametric model. So this P is indeed a function of zeta and another parameter, unknown parameter, say zeta. Okay, but this is infinitely dimensional. Because if you to completely characterize the distribution, you need not just the first two moment, right? Third moment, fourth moment, and infinity moment, actually. And so everything other than first two moment can be regarded as a noises parameter, infinite dimensional noises parameter. And so how you want to avoid that issue has to do with the information projection. Okay. And now your model space. So mu. So if you view it as a first example that we covered, then your mean mu is 0 actually, right? Because this is a random variable. So this random variable x, previously we just have a bx, right? So this bx, but this bx has a 0 expectation, but this bx contains unknown parameter zeta. Okay. So So let's first worry about how to do it for a fixed zeta. Okay. So if you fix zeta, then it's easy problem because that's exactly the same problem that we discussed in the previous example. So then but notice that if you view this Kullback-Leibler divergence carefully, you have something like this, okay? And then the denominator is a point mass, right? You have a empirical, so denominator is empirical distribution. So that means denominator can take a zero values outside the sample, realized sample, which means that which will create the log function to infinity. But you are interested in minimizing it. So that means whatever the solution finite. So to make this finite, that means you have to assume that your P will be have a zero mass outside the sample support. Okay. So that is basically what this message is about. So the problem is equivalent to finding the minimizer of this one, subject to normalized constraint. And so the second constraint is the constraint that comes from the moment constraint here. Okay. Now, the question is how to do information projection onto this space. The first question. And then once we obtain this one, how to estimate the parameter zeta. Okay. And now third question is what is the properties of the resulting estimator of zeta. So these are the questions, research questions. So first question is easy to solve because we already know the answer because it's basically the same as the first example. So see this is basically your Q space, the M plus space set is just this one. Okay. So this P is indeed actually omega, right? Completely characterized by omega. And then this is the basically constraint. And then apply I projection, like I projection over this space. Okay. And then in that case, we know the answer already, right? So this is exponential tilt that we learned. It's just the same as this was a px, right? pxi previously. Now we change it to u zeta, ui zeta. That's the only difference. Everything else are the same, right? And then of course this lambda star or lambda hat will satisfy the constraint. So that means this lambda will satisfy this, right? Because it satisfies calibration equation. You can view it as a calibration equation, right? So then basically it's the same problem. Equivalently, remember the dual, right? So let's go how we solve the same problem using the dual optimization formula, which is 14. So let's go back to 14. What is 14? So 14 is this. Okay. This is 14. And now mu is 0. Right? And phi is what? Phi is this guy. Not phi, psi. The psi is this guy with this bi is equal to ui zeta. Right? So now let's use this formula, this dual formula to solve our problem, which is this one. Exactly same, right? So it is a potential function for corresponding uh, to mu equal 0 to solve mu equal 0. Okay. Well, there's some tip, computational tip. I mean, mathematically, this is complete. Okay. But when you actually program and do computation, there's some, techniques, a lot of techniques. For example, usually when you take the exponential transformation, a little bit, if you think about that, right? If you in the convergence, if this is like say 20, what is the exponential of 20? It's huge, right? So maybe it's beyond the memory limit. So then you will have some problem. So so one way to avoid this problem is you always careful, try to make sure that whatever inside the exponential transformation is small. Okay. And one way is you subtract by the maximum of this guy, right? Subtract first, add and subtract. Okay, add and subtract, and then the adding this guy exponential of log is just can go outside, and subtract. Then after that, you this guy is small, will be small. Okay, so these are not really covered in the class, but if you do your coding, you always get this kind of problem. Okay. Second question is how to, okay, so this is basically eye projection, right? The information projection. Now, second question is how to estimate the parameter. So basic idea is, okay, now look at this. We now have lambda as given and theta is unknown. Okay, so that means this lambda will be completely determined by theta. Why? Because of this, right? So lambda is supposed to satisfy this calibration equation. So that means this is indeed a function of theta. And so you plug in and put it to your Kullback library. And then turns out that by equation 15, if you remember, let's go back to 15. What is 15? Here. So this is 15. And mu is 0, right? In our problem, mu is 0. So then Kullback library is just minus phi. So log n minus phi psi. Okay. So that is basically this guy. Log n minus psi. Okay. And then lambda is because we already profile. Now it becomes a function of theta only. And so we need to find the minimizer with respect to theta. Okay. So this is basically our estimator. So we first maximize, right? Previously, see, here minimize. Okay, so given sorry, given theta, right? Given theta, we determine lambda from 19, and then plug into our Kullback library, and then turns out that this is our optimization problem, which is actually maximizing psi lambda star theta. And because lambda star is indeed minimum for 19. So actually this is 19. Sorry. Okay. There's a typo. This is 19, not 20, not 14. Because 19 means this lambda star is minimum. Okay. So my point is you can write this guy as a arg max theta and min lambda of psi lambda and theta. Right? So this is this one. So this is a maximin problem. Maximin of the psi potential function. Okay, that's one way. There's another way, something called the ET-EL method. ET is same thing, E projection. And EL is used, so the difference is this step is the same, okay? So this is more like a modeling step. You modeling of omega. Okay. You determine the functional form of omega star, right? And as a function of lambda. Okay. Now the question is how to determine theta. And one way is just the profile. So replaced by P star theta. That's one way. That is this way. Okay, profile approach. Another way proposed by Shenak is that reverse the relationship here and then minimize. Because if you reverse it, then it becomes an M projection. Remember. So try to do something similar, close to M projection, MLE type estimation. Well, it turns out that these two methods gives the syntactically, first of all, they are different in the second order, but equivalent in the first order. Okay. Okay. So that is about parameter estimation. And now, once you have an estimator, then what kind of properties you can obtain? And there's basically the bottom line is you can construct some kind of likelihood, although it is not really a parametric approach, but surprisingly, you can eventually construct some kind of objective function that has the property of likely very similar to likely ratio statistic. So this is if L is log likelihood, then this is called Wilks theorem, right? And but turns out that even the semi-parametric model, you can develop the Wilks theorem. So that is very promising, interesting research outcome, especially in econometricians really like this kind of a problem because they hate making strong modeling assumptions like a normal and or gamma. They don't like this kind of assumption, but they are willing to accept this moment assumptions because without any assumption we cannot do anything, right? So we want to make an assumption, but we don't want to make a strong assumption. So then this is a reasonable set of assumptions that can be used. And also, I also have many research project with this kind of problem in survey sampling and missing data and causal inference too. Okay. And then section 4 is about computation. Even if no matter how much we know about mathematics and theory, if you cannot really do coding, right, then you you cannot graduate basically. So you need so this is I think worthy of mentioning because there's actually nested structure. You know what I mean? Because for given theta, right? Given theta, we need to completely lambda is completely determined. So basically, lambda is a function of theta, and then you want to your final objective function is function of theta only. But there's a lambda, so there's a something called loop. It's called a two loop method. So two loop computation. So there's an inner loop and outer loop. Okay, so inner loop is for given theta you determine, and basically we have some Newton we'll use we can use Newton method to solve lambda. Okay, so basically this is finding lambda for given theta k. Okay, outer means we want to update theta. Okay, and so then basically we know the loss function already. I mean the loss function or objective function you want to maximize or minimize is this psi lambda theta and theta. Okay, and turns out that uh, so if you think of it this way, so this is if you want to take the differentiation because you want to apply Newton method, you want to apply differentiation, right? Then how to differentiate? There's actually very interesting result. So basically, you difference. If you do that, then you don't have to worry about differentiating lambda. So there's actually another one, right? Because lambda, there's a two component, right? So you can differentiate theta, and how about the other one that turns out to be zero? That is called the envelope theorem. So I made an appendix. So there's an appendix, something called developing envelope theorem. So basically, if your objective function is something like this, okay, something like this, turns out that your differentiation is just the differentiating with respect to theta, and no need to worry about lambda, because the differentiation here, this term is zero by the definition because lambda is kind of boundary point, right? So this guy optimization, saddle point or whatever. So this will be zero. So you don't have to worry about it. Okay, so that's one thing. And then another technique that might be useful is something called the PFGS. So what is that? Well, so this is just a statement inner, okay, and outer. Inner is just E projection, I projection. So So computing how to given set how to compute lambda, right? Uh, Notation it's not big deal, but so this is a convex inner relatively. So this is basically as long as zero is inside your convex hole, then you can just solve it. I mean, if zero is in the boundary, then there's it's more complicated. But let's assume that this is zero is inside. Basically, um, then this problem is relatively easy. It's just this problem of solving lambda. In the outer, okay, outer is this one. So mathematically, right? Mathematically, this is clear, but when it comes to the actual computation, so inner part is actually easy. Inner part is just computing the Newton method, but one thing is that this alpha. So usually alpha equal to one. Alpha to one is the classical Newton method, okay? But sometimes you want to reduce your alpha a little bit to make sure that you increase the likelihood or something like that, okay? Because if your learning rate is too high, then you might be actually your update doesn't really improve. So you want to make sure that your update improves. Okay. So auto maximization, minimization. So this part is okay. So this part you can compute from the envelope theorem. And now what you want to do is you want to approximate the inverse of this Hessian, okay, but without computing the inverse, basically, because the computing the inverse is computationally expensive. Okay, so this technique, something called this PFHS, is a numerical way of computing the inverse matrix. So this is approximation of this guy using some technique. Basically, I have actually appendix 2. So what is this inverse BFGS update? Motivation is that you want to solve this. So what is this? So S, because Y is change of your tangent function, okay? And this is Hessian, right? So you want your tangent to be changing the tangent to be Hessian. I mean, not Hessian, Hessian inverse, right? So you want this to be approximated by square f times sk, right? That is kind of numerical way, you know. So the left side is the change in your tangent, right? The right side is this is a change in your zeta. Okay, and then basically this will kind of give you, so if you divide it by here, right, then this is a kind of numerical way of visualize, I mean, understanding the Hessian, but you don't want to compute the Hessian directly because that's too much. And so then basically you just numerically evaluate the changes in the tangent and then try to approximate the your current Hessian inverse Hessian function so that you can compute it in your code, something like that. So I think this I also learned these techniques recently and found think it will be very powerful in many problems, including this particular uh, problem because it uh, use UK is a function of zeta. So that means we have a kind of nested structure in the optimization. So these two you know loop, inner and outer loop technique uh, should be used. And so, but I think nowadays all these computational tools are quite well understood in the literature and so you can maybe consult with the ChatGPT and help get some help. Then I think uh, you can also become an expert. So I think that's the main thing. You can read this slide and try to figure out if you are interested. And if not, I will just take any questions and stop finish our class today. Okay. Yeah. So as you can see, if you learn, try to read this paper and start from there, is very difficult. But if you start with a specific problem, right, and then maybe it's easier. And you know the context, then if you read the paper, you have a much better understanding. Yeah.